Okay, uh, welcome back class to this online lecture for our optimization techniques masters course. Um, there are many students amongst you. They came to me, and I feel that there is a lot of confusion around the simplex method. That's why I think a few days ago I shared one of the links of a book. So I will go through at least one example for all of the topics, uh, and then we will continue for the remaining part of this chapter, and we will finish this chapter in this week's lecture. So the book that I discussed, it is you can search it on the Google, for example. So you write over here Cengage, and then you write chapter 9. It's the chapter 9 in this book, and you write over here simplex. Okay, so linear programming, Cengage, and it's cengage.com. So when you click on this link, it will open the chapter 9 of the book. So when this opens, I have already saved it, so I will show you from there. So this is the chapter 9, linear programming. So this is it. I have already saved it with me. So the number of pages are 63. Let me check. Here with me they are 54. So is it a different one? I feel it's the same. I think there are different versions for the book, but it is the same thing because they have the same example. Okay. So this is with me over here. It is saved. I will try this one also, put it online. So here I will discuss some of the topics with you from this. The linear programming itself, how it is used, and how it can help to in our daily lives. So basically, in the linear programming, to solve the linear equations, what we do is we uh, have set of equations that represent constraints, and we can solve them for some specific purpose. We did not discuss the practical aspects, but these things are used for many different areas, like for example advertisement, product advertisement. For example, on YouTube you are watching a video, so based on your constraints, your country, your age group, and other properties about you that the YouTube collects, what advertisement it can show to you, that is one of the optimization problem. Again, it can be used in the industry where we have discussed such type of problems where we can try to predict what is the minimum amount of steel that is wasted. Also the optimization that it can be used in the software industry, in the software, and hopefully this is the area that you people will be focusing in your degree regarding optimization. And finally then there are the uses in the healthcare applications to find out the target heart rate, which one is the best. And also it has got the uses in the restocking of ATMs. For example, ATM machine, try to predict when it will finish up the cash inside and when the person should come to fill it up. So I will quickly go through this first part. You did it before. So this book is really nice. I recommend that all of you must go through the examples in this book. So it has got over here the linear inequalities, how you can draw them. So these are some of the examples you see over here for the inequalities. Okay. So what we do is try to solve the linear inequality. For example, it has two variables x and y. So we try to solve it. So solving means that whatever point we select for the x and y, it should satisfy this equation, as you already know. For example, this equation 3x minus 2y is less than 6. So for the point 1 comma 1 means x is 1 and y is 1, this equation definitely holds. So we, like this, we can draw or sketch the inequalities. So lots of them, they are coming next, we will see. So inequality can have this symbol, less than or equal to, or greater than or equal to, or some other versions. So these are the four possibilities you see for the inequalities that are the most frequent ones. You see less than equal, greater than, or greater than equal. So you see a small example over here. Example number 1, how to sketch and the graph for this. So this is a simple case, x greater than minus 2. So it is basically this line they have drawn over here. So this x equal to minus 2 means that your x position is at minus 2, but the y is not defined, means that y can take any value from minus to plus infinity. So this equation means that all the points, so it is greater than symbol, so it means that all the points on the right of this line is not included, that's why they have shown it as a dotted line. In the second equation, you see y less than equal to 3, it's a solid line, and the area that is inside that satisfies this equation is below this line. Okay, so I think this is very simple. There is another one example given, x minus y is less than 2. So x minus y equal to 2, you can try to find it out, plot it out. So the plotting method you already know. First make x equal to 0, then y equal to 0. It will give you 2 points. You draw the line, and after that you select the point 0, 0, that you will decide on which side it is. It is on the correct side of the line or not. So in this case, for example, you put over here 0 minus 0, it is 0. So 0 is less than 2, yeah, that's correct. 0 is less than 2, it means that 0 is on the correct side of the line. So it means that your area representing this inequality is the blue one. So quickly going through, there are some more equations given over here. Instead of one equation, we can have system of equations, and if you know, we have already discussed that we always have these two equations, x and y greater than or equal to 0. So with these four equations, we have drawn over here one area that's shown to you. Clear? And then there are some more. Solving the inequalities means that if you have three equations, you plot them up, and then after plotting, you will try to find out the common area. So for example, over here you see uh, x minus y less than 2 is this one. So it is x minus y is less than 2. It is represented by, I think, this line, this dotted line. Okay, and x greater than minus 2, it is the line that is shown by this horizontal line, the area on this side, greater than minus 2. And then the final one is y less than or equal to 3, it is this one that's shown over here to you. So these are the three lines, the three inequalities. When you combine them together, you get this area which is together. So try to solve it yourself, then try to find out the 3 points or the 3 corners for this. How you can find the corners? We have discussed in the class. You will consider them as a line, not as inequality, as a straight line. And you will solve those equations. Each two equations, when you solve, it will give you 1 point. So you will have 3 points, 3 corners, A, B, and C. And the region inside this line, these 3 lines, this triangular region, it is your feasible region. Clear? Now going next, so I go through quickly because I feel this is already clear to you people. I want to reach that simplex method. So sometimes the intersection of the two lines, it will not be a vertex that you are interested in, because you see over here, this one is not included in the area. So you can make sure, because easily you can make it clear that this is included or not, because this corner point, the coordinates of this point, do they satisfy all the linear inequalities or not? If they satisfy, then they are part of the feasible region. If not, then they are not part of the feasible region. Sometimes it happens that two equations, they don't have any solution. So it's not to have a solution means, what does it mean? It means that basically they don't have anything common. So you can't find their common intersection point. So here is an example. X plus y greater than 3 is this blue area, and x plus y is less than -1, it is this pink area. And you can see that these two areas are mutually exclusive. They are far, far apart. There is nothing common between them. So it means these two equations don't have anything in common. Clear? There is another equation given over here. These two equations over here, they create an area which is unbounded region. So here you have got some common area, but there is no closing upper limit. So it is open and it's going like this up to infinity. Okay. So these are a lot of different examples of the regions that you can have. So example number 4 is given about the application of the system of inequalities. So let's go through this. Here you are given a liquid portion of a diet that is to provide at least 300 calories and 36 units of vitamin A and 90 units of vitamin C daily. That's what you want to have. That's your requirement. 300 calories, vitamin A 36 units, and vitamin C 90 units. Clear? So how you try to achieve this daily requirements? You can take the cup of a drink X. So this is a dietary drink X or a dietary drink Y. The drink X, it provides 60 calories and 12 units of vitamin A and 10 units of vitamin C. Whereas the cup Y, the drink Y, it provides 60 calories, 6 units of vitamin A, so it's less as compared to the other drink, and 30 units of vitamin C, so it's all more, 3 times more than the other drink. So you need to set up a system of linear inequalities, and then you need to describe the minimum daily requirements. So this can be a typical exam question that I gave you before. Something like this can happen, can come, where you are asked some question in a paragraph, and then you need to transform this into a set of linear equations. So what you need to do is, before you start solving the problem, you have to clearly define your variables. Without defining variables, you will lose a lot of marks. Be careful. So here you define variables X and Y. X is basically the number of cups. So remember, these variables are mostly something that you want to predict, you want to find out, to calculate. So X here, it represents the number of cups of drink X, and small y represents the other drink, how many cups you need for that. So based on these X and Y, then you try to make an equation over here. Just pause the video, go through these equations. What do you think? What does how it comes like this? So for the calories, you see over here the equation given is 60x and plus 60y, that should be greater than or equal to 300 calories. So x and y are the number of cups for drink X and drink Y, and you multiply it by 60, which is 1 cup calorie for 1 cup, and this gives you the whole equation. Similarly, you have another equation for vitamin A, which is 12x and 6y, that should be greater than or equal to 36. So keep on going like this, and then you make over here the complete equation set. Remember, you always put the two equations for non-negativity constraints. So this will give you the graph that is shown below this one, and you see over here the requirement, the feasible region is shown by this blue area, and this is the lower limit of the feasible region. Clear? So any point that is inside this blue area, inside this shaded region, it meets the minimum daily requirement for calories and vitamins. So you can select any value over here, for example 3 cups of drink X and 2 cups of drink Y. So for example 3 cups of X and 2 cups of Y, that will give you this point. So it will satisfy your 300 calories, 48 units of vitamin A and 90 units of vitamin C. So it just exactly fulfills the requirements for calories and vitamin C, but for vitamin A it exceeds the minimum requirements. Clear? So similarly you can have some other set of equations that can be used, for example like the heart rate monitor. It can have many different graphs for your different health parameters, and it can give you the ideal range of your target heart rate. So here there are tons of exercises. Solve them, do them. These are important. Some of them maybe they can come in your exams also. So going next, there is another set of examples. Here you are given the graph. So you are given the graph and you are asked to describe the system of inequalities for these graphs, for these regions. Okay, so the opposite. Then there are some more set of problems given. Here you are given some vertices, some points, corners, and then you have to write down the set of inequalities that describe these regions. So think over it. This is a little bit different problem. Think over it, how to do it. There are many more problems given. Some of them are descriptive problems. These are the ones that I like a lot. So expect something like this in the exam. So there is a given over here some description, textual one. There is 59, then 60, and then more over here. Different types of problems. Take your time and do it. Very important. And finally, then there is a small capstone project they have given, where they describe about a system with these 3 equations, and you try to find out. I leave it. I think this will be difficult, but those practical problems are more interesting and they will make you more involved in this course. I suggest do a lot of them. Then comes the linear programming part. So till now we saw initially how to make graph them. Now the second part that comes is when you have 2 variables, how to deal with the equations. So when you want to solve a linear programming problem, we normally call this as a process called optimization. So many applications in the business economics, they involve this thing where they want to optimize something. And normally always there is some sort of, for example, you want to reduce the cost, or you want to maximize the profit, and or you want to minimize the use of the resources. These are some of the things, and we already know it. It's linear programming. So always there are 3 things, if you remember we discussed. There is the objective function, and then there are set of some equations, linear inequalities, we call them constraints. So objective function, for example, it is normally in this form. Okay, so one method for solving these things is you have already seen. It's the graphical method. So you have the objective function and the constraints, You try to solve them, try to find out the equations. So you try to find out, you plot them. For example, in the case of graphical method, you will plot them, for example. So you see over here, these are the four equations. And then what so you already know how first you will convert these inequalities to equations, then you will plot them, then you will try to find out the corners, and from the corners what you will do is you will try to find out which corner has the maximum value of z. So you see over here this one, corner number 2 and 1. So in the case of maximization, it is giving us the maximum value. Clear? So you already know this, all this practice. So z equal to 2, z equal to 4, 6, 8. All this you already know. This is just giving you one extra attempt. One other equation for maximizing, and here they have given the solution also. So the good thing about this chapter from this book is that you will get a lot of examples, and the solutions are given. So it will help you a lot to grasp your control on these problems. Many of you ask me questions, and I feel the others who did not ask, they will have many questions in their mind. One bigger question is that, okay, we understand, but we are not sure, we need practice. So here you are seeing this practice. So make sure you take this time. You people are also locked down in your homes. So use this time to learn this effectively. So here is a minimization problem. This time we want to minimize. So again you are given with some constraints, and you have the objective function. So here it is your region. So you draw the region, and then you know that you want to minimize. So in this case, when you have the graphical method, you just take the points. So you have 3 and 3, 6 points. For these 6 points, you try to find the z value, and the minimum value of z in this case is 14. So that is your best solution, which is x0 and y equal to 2, which is, I think, this point. Clear? So what I suggest is you take a blank page and cover the solution part. First look at the question, solve it 100% yourself, and then you try to look at the answer. Okay, here is another minimization problem. uh, this is different minimization problem, and here you see the graph they make. From this graph you see over here, so this is minimization or maximization. So I think this is maximization problem. So this is the maximization problem, and what they want to say is that these are, maybe they don't even explain the equations. So thus they want to explain over here that the z value, so this is the case we have done in the class, the z value, that is 100%, the objective function is 100% parallel to one of the constraints. So in that case, all the points on this line, they are feasible. All the points that occur on this line, so means the values of x and y that satisfy this whole line, they are the valid solutions. So values, for example, between x equal to 2 until 5 and y equal to 1 until 4. No, yes, 1 until 4. So all these values, they are valid solutions. They will give you the best value of z. But again, instead of going into too many points, we only select the two corner points, because corner is always one of the optimal points. So in this case, you will see both these corner points, they give you the same z value, which is 12 in this case. Clear? Another maximization problem. So you see over here, one more thing that's given is that they have given a website. It's called over here, the name is given larsonlinearalgebra.com. So I have already opened it. So here it is, Larson Linear Algebra. So if you go on this website, they have given some sort of interactive examples on this website. So click on these examples. So this is a nice book. They have got some lots of examples. That is the best thing about this book. You will see a lot of material on the internet, and many times they don't explain the things. So here you have, for example, chapter number 9. And in chapter number 9, go and check the section number first. Section is important to know for you. So this one is 9.2. Okay. So in 9.2, I want to check, for example, example number 4. Whenever there is this thing written, so the example, interactive version of the example is given on the site. So interactive examples, section number 2. So it will take a little time, and then you click over here, example number 4. Only 4 is available. Other examples don't have graphic. So it is only for this example. So when you click on this go, it will show you a link to a file called the CDF file. So let's say you can say a name they have taken from PDF. So PDF is portable document file. This is CDF, I think, means computable or computive document file. So this is a special type of file format. For this you will need a player, CDF player from Wolfram. It's available here, but it's a big file. So it's almost 1 GB. So when you click and download this file, so for example, this is file number 51. I have already downloaded. So if I open it for you people, so how it looks like. So this is it, 51. So when it opens, it will show you a small interface where you can play with the numbers and you can see what changes occur for that problem. So example number 4, it is about an unbounded problem where you have got an objective function and then there are set of constraints as always. And here when you draw this region, so why is it not opening? So it's a big software, it's taking time. Okay. So when you draw this region, it is this over here, it's a blue shaded region and it's unbounded, you can see already. So for this, you try to solve it. You want to find the maximum value of z for this region. So because it's a maximization problem, maximum in this case is unbounded. That's shown over here in this problem. So what is important about this CDF file is that you can change these parameters. For example, you make it 2. Okay, z is 2 or z is 5. What will happen? So 4. And you can change the constraints. You can play with the constraints. Say the constraint has totally changed the feasible area. So this is what I want you to practice a lot. Take these equations and plot them. So you see here it gives the different versions of the plottings and it will give the different feasible areas. You play with it and try to solve it yourself first and then you practice over here. Okay. Different feasible regions it will give you and it's showing you already the answers. Okay. So it's showing you that the maximization problem, if it's maximization, then it's unbounded. But for minimization, it's giving you the value of z, which is 29/7. And this value occurs as a point at a point which is 13 fraction 13/14 and then 3/14. Clear? So this is what occurs. I don't know, maybe I try something else. Now here you see Here it is giving you some values. Maximize only occurs if I don't know what it's doing. 92 over 3 null unbounded, and minimize occurs at this location. So this needs to be checked in more detail. Here maximize is unbounded and minimize occurs at this location. So I suggest go through this example. It will help you grasp the ideas more concretely. So this was your unbounded graphical problem. Here is another example. So there are tons of examples. I suggest do it. It's must. It will help you because in the exam on the average, remember, you will have maximum 20 to 30 minutes for one problem to solve completely. The final exam will be only 2 hours exam. You have to do everything in 2 hours. So one problem will get 20, maybe 25 or maximum 30 minutes, not more than that. So here you see, and this is the same problem that came before. 3 equations plus 2 non-negativity constraints, and they try to plot it, and for this they want to, this time they want to minimize. So this is objective criteria given. So this time they have added something. So it is the same problem you saw last time, but last time it was only to draw the constraints. Now they have added something over here. Yeah, so they have given over here. Now assume that the dietary drink X costs, so they have put the cost now. So the dietary drink X, it costs $0.12, so it's almost 12 cents per cup, and drink Y costs 15 cents per cup. So how many cups of each drink should be consumed each day so that you fulfill your requirements and at the same time you minimize the cost? Clear? So you can already know that this is the minimization or cost optimization problem. So the criteria Z, or they have written C, it is equal to this. This is your objective function. And for this equation, you have got 4 points, 4 corner points. You take these 4 points and put it in the equation, and you will see that the minimum value occurs at point number C, which is 3 and 2, this point. That's minimum. Clear? So the overall minimum cost that occurs per day is 66 cents. So this is another application of optimization techniques that is used by the banks. The softwares, they are used by the banks based on the customer behaviors and other issues and other data, for example weather and if there is a holiday or not. The banks, they can predict when they need to fill the ATM machine again with the money. Clear? Here are some tons of examples given to you related to linear programming. So it will give you practice, and now you will not complain that you don't have any examples to solve. Okay? So for all of you, for Asim especially, now there are many examples. Now maybe you have time also, I don't know, but you are in hospital. Hospitals are not on holidays. So take your time and try to solve these things. Okay? So you see over here more problems. The first problem, just go through it, what they ask. Exercise 1 and 2, find the minimum and maximum value of each of the objective function and where they occur, subject to the constraints. So constraints are given, you try to find out the minimum value and maximum value for the Z. Okay, they even have given you the graphs themselves. In exercise 3 to 8, this time they don't give you graph. You have to sketch the region determined by the constraints. And then what you have to do is you find the minimum and maximum values of the objective function. Clear? So tons of examples for this. And then you go 9 to 14. Here you again find minimum maximum values, and yes. So the constraints are given. Z value is given like this. So these are a lot of examples now. The Z value is only given here, but the constraints are common. So constraint 1, constraint 2, so two constraints, and 3 and 4 are the non-negativity. Okay. Then they have given some unusual characteristics of the constraints. Try to look at these problems. There are so many. And then there are the English based problem, descriptive problems. These are the ones that are my favorite. So try to solve them yourself as much as you can. And then we move on. Next, so here are more problems. Then comes this one that for which many of you came to me, the simplex tableau. Okay. So for the tableau, how it works, the simplex tableau, again the same things. You have the same set of the problem is defined in the same manner. You have objective function, and then you have the constraints, and the objective function and the constraints both, they are created from decision variables. So decision variable means the variables that are used in these equations. So in this case there are x1, x2. Okay. Always in our problems we have the inequalities, and we convert those inequalities into linear equations. So when you convert inequalities into equations, you add over here some extra variables. So depending on the type of the linear inequality, you will convert it into, you will add different types of variables. So for example, if it is less than or equal to, then in that case you will add, so less than or equal to, so listen carefully, this point. Less than or equal to means that this side over here, minus x1 plus x2, it is maybe equal to 11, or it can be less than 11. So it can be 4, 5, 6, up to 11, it can be 11. Okay, but not more than 11. Now if it is less than 11, so it's a lot lesser, then you need to add a variable over here, s1. This variable s1 will represent the value that is missing from the equation. Only when you add s1, then you can make this equation as an equal to sign. You can convert it into inequality, into equality. Okay. So when you are removing this inequality, you change it with an equal to sign. You can only do it when you add a slack variable in this equation. We call them slack because they represent the slack, or slack means the word slack in English means the deficiency. Or go on, maybe check on the Google the meaning, suitable meaning in Arabic for you. But it means deficiency, something that's less. Or you can say the word in English, lack. Lack means less. Okay. So you do like this, you add the slack variables, and we proceed. So this is more the standard equations given to solve this. Next, what we do is that based on this slack you have added, now you have the constraints given as equalities. You go and you try to create your basic solution. So for your simplex tableau, you want to make a tableau. You will have the basic and non-basic variables as we discussed in the class. So here it is. For this objective function, this time in this book, the objective function they have written in the last, but in our book, in our slides, we have the objective function on the top. Okay. and rest everything is same. So you see over here S1, S2, S3, both of all three of them are 1 1 1. So if you see these three, they are our basic variables, and x1 and x2, they are our non-basic variables. Okay. So when we start initially, so remember z equal to 4x1 plus 6x2, that's our objective function. But you will convert it into an equation having right side equal to a constant or a 0. Okay. So when you make it like this, you will have z minus 4x1 minus 6x2. That's how it comes to you, this z equation. So your initial starting point when you start your problem, so the initial simplex tableau, for that you have the basic variables s1, s2, s3, and the non-basic variables are x1 and x2. These two are non-basic. Okay. When you start with this solution, so you have these values given. So from this equation you can see easily that s1, s2 and s3, they are 1. So when your x1 and x2 are 0, so one of your starting solution can be that you put these are non-basic. So non-basic, you can just like you can say they are non-basic means not important. So they are not important. You can put them temporarily. When you make these two 0, then in that case s1 becomes equal to 11. When these two non-basic are 0, then your S2 is 27 and so on, S3 is 90. So this is your starting basic initial simplex tableau. This is your first bad solution. Okay, this is the starting point. So one important thing that's shown in this book, this is important, I think I didn't mention in the slides, is that the solution you can represent it like this also. This is a very good manner for representing a basic feasible solution. So you write over here all your variables and then you write equal to and you write the values in the same sequence, tartib. Okay. So here it is 0, 0, 11, 27 and 90. This is your bad solution, initial one. Okay. So how to check if this solution is good or bad? To perform an optimality check. So if you remember, pause the video and give me the answer of how to check if it's a good solution or bad one. So the bad solution is good or bad, you perform an optimality check for the solution that is represented by the simplex tableau, and you look at the entries in the bottom row or the Z row. In our case, it's the top row of the tableau, and you look if there are any entries that are negative. If there is any entries negative, then the current solution is not optimal. So look over here, the Z row in this case over here, it has got two negative values. Negative value means it is not optimal and you should continue. Okay. So we go on, and now we have to decide that this is the critical part. This is the part where all the questions I get. Pivoting. Okay. Now you have decided that your solution is not optimal. How to decide what we should do next? That is the case of pivoting. So for the pivoting, you have two issues. You have to decide the entering variable and the leaving or departing variable. Okay. So entering variable is the entry that corresponds to the least or you can say the most negative entry. Okay. The entry that is negative and it is the highest negative value. So that will be your entering variable that you will select next. So in this case, so you see in this case out of these x2 is your entering variable because its coefficient for the z entry is -6. So this is entering variable. When you have decided this entering variable corresponding to the corresponds, then the departing variable or leaving variable is the one that corresponds to the least negative, least non-negative, means the least positive value, the positive value that is smallest in the ratio of b over a. Okay, where b is your last row, the constant. So that's what is over here. The b is this row, and you take the ratio of this b with the entering variable row, entering variable column. So the column b, you divide it by column x2, that will give you the ratio. So 11 over 1, 27 over 1, and 90 over 5, and you will select the one that has the minimum positive value. So here it is, it will come next. So you try to pivot to find the improved solution. So here we start. So this is our current solution. You see 0, 0, 11, 27, 90. And from this solution you know, so I wasted time above. This is here. We find out the minus 6. Okay. From this minus 6, then I try to find out the ratio of the B column and the X2 column. This ratio is 11, 27, and 90 over 5 is 18. So from these three, I select the least positive value, which is 11. So it means that S1 will be the leaving variable. Okay. So we kick out S1 and we enter X2 into our basic variables. Okay. So this is the final solution for this one step. So the one step occurred over here. And what happened is that before pivoting, this was the table, and after pivoting, the tableau becomes like this. Now what happens over here, this is the point of confusion for many of you. This is the entering variable x2. This one over here, s1, is the leaving variable. Okay, clear? So intersection of this row and that column, that will give you the pivot variable. Pivot variable is 1 in this case. Okay. Now remember, any variable that enters into the basic solution, it must have the structure like this: 1, 0, 0, 0, 1, 0, or 0, 0, 1. Okay. That is must structure that it must follow. Okay. And we want to put a 1 in this location because this is the place from where the one of the variables has left. So because S1 is leaving, so S2 and S3 have the ones in these locations. So now we need the new variable X2. It should have the 1 in this location. Okay. Not in the other locations, only this location. That's why we select this entry as the pivot element, intersection of column and row. Now if this value is 1, that makes your job easy. If it is not 1, make it 1. How to make it 1? You can divide anything by the whole row. So for example, if this value is 7, you will divide the whole row by 7. Okay. So it is already 1, so you don't need to do anything. The next step you will do, that's confusing everyone or lots of you, is that remember, you want to make it a basic variable x2. Okay. So the basic variable should have this structure. So the top one is 1, then the below two should be 0 and 0. Clear? How to make it 0? That's the question. That was the Gauss-Jordan elimination method. So how to make these two rows 0? Remember, always you are allowed to add or subtract the rows from each other. Okay. So for example, if I want to make this thing 0, okay, and these rows are represented by, for example, this is R1. It's difficult to write here. R1, and this is R2, and this is R3. Okay. Now if you see over here, if I want to make this value over here 0, one best thing to do is that I will simply say that my new R2 or R2 dash is equal to R2, the original value, minus R1. So R2 is 1. 1 minus 1, how much? 0. Okay. But remember, I cannot subtract only two values. I have to subtract the whole row, including the last B value. I have to subtract the whole row from the upper row. Okay. So what it should be? So you subtract, to subtract, you change the signs of the upper row and then you just add them over this row. So this will be 1 minus 1. So it will be 1 plus 1, which will be 2. This will be 1 minus 1, 0. This will be 0 minus 1, it will be minus 1. And here it will be 1 minus 0, it is 0. 0 minus 0 is 0. And 27 minus 11, it will give you how much? It will be 16. So 16 will come over here instead of 27. So now check over here. Come to this place. 2, 0, minus 1, 1, 0, 16. Same thing that I described, it's done over here. What will be the reduction method for this row? It will be R3 minus 5 times R1. Okay, so that's what is happening over here. R3 minus 5 times R1. And also you have to apply the same things over here for the Z row. So for the Z row, what you will do is you want to make it 0. Remember, the basic variables must have zeros everywhere. So when you want to make it 0, this time it is minus 6, so you will add plus 6. So you will multiply this whole row with the 6. So it will be 6 R1 and you will add it to this row, which is RZ row. Okay, so they have called it R4. So you will do R4 plus 6 R1. That will give you this thing. So now when you do all this thing, you first decide entering variable, then you decide leaving variable, then you decide the pivot element, and you do these reductions to complete the entering and leaving. Okay, now you are entering and leaving, it's done. And from now onwards you have three variables that are basic. Basic variables are S3, S2 and X2. So here on the right, or in our slides case, it's on the left. Now you will change the name. Before it was S1. Now you will write X2. Now one step of this whole method, simplex method, one step is complete. This is one loop. Okay, at the end, I like this method. You write the answer like this. So for the values, for the basic variables, for all the variables, basic and non-basic, the solution is this. Now you will continue again. This time you can even calculate the value of Z. If you remember, last time the value of Z was 0. Okay, remember, Z was 0. It's not given, but it was 0 here. Now for this method over here, you get the value of Z, which is 66. We keep on doing this same method, and this time the solution is not optimal because the bottom row has another negative entry. This time this one is negative, minus 10. So x1 is our entering variable, and the leaving variable we will decide based on the ratios. So the ratios we take for this column x1 with b. So it is 16 divided by 2, this one divided by 2, and 35 divided by 7, and that gives you 5. Okay, so you take these values, the value that comes out is 8, 5, and the third one they haven't chosen. Why third one is 11 divided by minus 1, which is minus 11, so they don't choose it because we need the most we need the smallest positive value. So out of these three ratios, the smallest positive ratio that comes is 5. So S3 is basically your leaving variable. So x1 enters, S3 leaves. Okay, so we choose again the Gauss-Jordan method. So here this time the pivot element will be 7. Okay, so for this 7, what we do is we will first make it 1. So how to make it 1? Divide the whole row by 7. Okay, so it will become 1 0 minus 5 by 7 0 1 by 7, and it will be 5. Okay, so it is I think given over here, this row. Okay, so first step, this is your original one. You make the pivot row pivot element equal to 1 by this operation, and then you remember the next step is that the three other rows you want to make them 0. So how to make them 0? They have given these operations here. Please go through them. First solve it yourself and then you see the answer over here. It will make all these rows 0. And now if you come to this to the tableau, the values you see over here, you have got x1 x2, they are basic variables, and s2 is also a basic variable, whereas s1 and s3 they are non-basic. Okay, so when you check the non-basic variables, you check the z row. If it is negative, so it is still negative, minus 8 by 7. So you will not stop your iteration. This was your second loop, you will continue. Okay, so s1 is your entering variable. The departing variable you will select this time, which is you will decide it based on the ratio. I don't know, they have taken the ratio over here. The ratio they haven't shown. So you will calculate the ratio, and based on that you decide s2 as the leaving variable, and this is your pivot element. So pivot element, again same practice, you want to make it 1. How to make it 1? Multiply the whole row by 7 by 3. Is 7 by 3, you multiply it with 7 by 3. So keep on doing, this is it. And then we do other operations, and finally we get this value, and this time there is no negative value in the z equation. So it means that our solution is optimum, and the best z value we get is z equal to 132. So you see we had over here 3 iterations. We started with z equal to 0, we went to z equal to 66, then 116, and finally 132. And basically again same thing, we started with 0 0, same as we saw in the slides. We started with 0 0, we go to 0 11, this corner, then 5 16, and then 5 15 12. So we go around the surface of the corner of the feasible region. So these were the steps that were given. This chapter, this slide, the material given here is in a lot of details. I don't think you will get more detail than this anywhere on the internet. This is the best possible. So go through it. There are lots of examples given. Try to solve it. Okay. So here is another simplex method given, but this time these are 3 variables. So 3 variables, I will leave it to you. Try to solve it and see if you understand it or not. Okay, many steps. Again, for these examples, the examples where it is written that there is a interactive version available for this So you will go to the slides and you will go to the website and check. So it is, for example, which section? 9.3 example number 2. So 9.3 example number 2. So section 3 example 2. File, this is 52. So I have already downloaded it, 52. So here it is. They have given the simplex method, objective function, and the constraints. And the simplex tableau for this problem are shown below. And the pivot values, pivot entry is boxed in red. Okay. So it shows a lot of different steps in the problem solving. And the important thing is you can change these parameters. And in the example, in the exam, I can give you some problem by changing these values, and you will have to deal with it. You will have to solve the problem. Clear? So this is given to you. Just try to see if you understand it. So these are the three decision variables, three decision again. So this is a business application given over here. So another one, very nice. The manufacturer produces three types of plastics. So plastic type A, B and C, and it is used for different types of products, for molding, trimming, packaging, and production time is given. So you have to take this problem, and then we make the constraints, and then it is used to solve for the criteria for the objective function. So you see many steps. Another business application. So lots of applications. Now you people should have the courage to go through, and then there are exercises. These are the solved ones. Then there are exercises. So it's a huge set of material. I don't think you can ever complain again about the problems. So I think there are a lot. Okay. Then comes the minimization. Again, minimization. Many of you ask the problems. We need examples. So minimization examples are given here. You see, you want to minimize this objective function. Constraint is given. So what we want to do is, so here they are using dual. So leave the dual. You didn't study the dual. Duality principle we are not going to work for now. So example 1, objective function, minimization problem, dual problem, leave it. If they are doing it by dual, you select some other problem. 216 and I don't know if they are doing by the dual or the direct set of equations, but the main theory is same. The only difference in the case of minimization and maximization, the difference comes when you want to select the entry variable. Entering variable selection is different. All the other steps are same. So here it is. So this is minimization, but they convert it to dual. So dual is not good. I don't want you to go to the dual side. They are doing all of them like this. So entering variable, they decide based on the largest negative value, because they convert it into a dual problem where the minimization problem is converted into a dual maximization problem. Okay, so it's not something you people have studied now. So take these problems, try to solve it yourself. The only difference is that at this step, the entering variable, you will only choose that variable which has the, for minimization, which has the largest positive coefficient for that row. Clear? Here there are some more minimization problems given to you, a lot of them. So go through them, try to see if it makes sense to you people. Then there are mixed constraints. Mixed constraints I don't think you will be using for now. Another thing that comes, okay, I will discuss that in another video I will make, and I will discuss the surplus variable. I think it's enough for now. I'll take a break and then I will discuss with you people the remaining topics for simplex, the M method and the